Hola, buenos días. Sean todos bienvenidos a este webinar. Por favor, ¿me podrían confirmar en el chat si me escuchan bien? Aquí deben tener la opción a la derecha del chat y las preguntas. Hola, hola, ¿me escuchan bien? Ok, me están avisando que se escucha y se ve bien. Bueno, vamos a esperar un par de minutos a que lleguen más asistentes y luego arrancamos con el webinar. Bueno, ahora sí, vamos a arrancar. Buenos días, bienvenidos a este webinar de soluciones analíticas, Analítica del Pacífico, Grupo Analítico Centroamericano, representantes de Thermo Scientific en Argentina, Perú, Panamá y Guatemala. Este webinar está titulado Espectrometría de masas de relaciones isotópicas, nuevas aplicaciones. Para este webinar tenemos el placer de tener acá a Darren Tolstrup, quien es el líder de ventas de espectrometría de masas avanzada para toda América. Darren se unió a Thermo Scientific en 2010 como ingeniero de servicio para toda la línea de espectrometría de masas avanzada antes de pasar a ventas en 2017. Darren es doctor en geoquímica de la Universidad de California en Santa Cruz. Y después hizo postdoctorado en cosmoquímica en la Universidad de California en Davis. Y también ha trabajado como científico de investigación forense nuclear en el Laboratorio Nacional Lawrence Livermore. Este webinar va a durar alrededor de 45 minutos. Pueden ir haciendo las preguntas en la sección que pueden ver de preguntas específicas para eso. Pueden ser en español, yo después se las traduzco a Darren. Eh, También, bueno, esto va a quedar, después lo vamos a subir a YouTube si quieren verlo de nuevo o alguien que no pudo asistir. Y también si alguno está interesado en el certificado de asistencia, se lo podemos preparar a petición. Nos hacen llegar la solicitud y le hacemos llegar el certificado. Bueno, ahora los dejo con Darren. Eh, Darren, you can start.
Thank you. Thank you. And thank you for joining today's presentation, where we will cover a few forensic applications of isotope fingerprints. All materials from nature, and including industrial processes, have a fingerprint, which is a unique chemical signature within their structure that gives them an identity that is different from everything else, just like our own fingerprints. To visualize this fingerprint, isotope ratio mass spectrometry is used to measure stable isotopes of common elements in order to identify the isotope fingerprints of those materials. And I apologize, this is going to be a very simple slide, and then we'll move on, but I just want to go back to basics for a second and say that this isotope fingerprint is based on the fact that all elements are made up from atoms, which consist of protons, neutrons, and electrons. Atoms of the same element always have the same number of protons, but they can have a different number of neutrons. Atoms with the same number of protons but a different number of neutrons are called isotopes of an element. Below, we have an example of the two most abundant isotopes of hydrogen, the lightest element. Protium and deuterium have different number of neutrons, and so they're distinguishable from each other. And they also have very different abundances. Protium is the most abundant at 99.98% of all hydrogen, and deuterium is very rare with an abundance of only about 0.02% of all hydrogen. The hydrogen isotope fingerprint is the very small variation in the abundance of this ratio between these two isotopes of hydrogen in a sample. In this presentation, we're going to focus on stable isotopes rather than radiogenic or even radioactive isotopes, because stable isotopes are safe to work with and they contain a lot of very useful information. The five most abundant and common elements used for isotope fingerprints are carbon, nitrogen, sulfur, oxygen, and hydrogen. All of them are fairly abundant in organic material, and they all carry unique information about different natural and synthetic processes and sources. Isotope ratio mass spectrometers are the instruments used to collect these isotope fingerprints. IRMS systems are composed of a mass spectrometer, you could think of it as a detector, if you will, and connected to this is one or more sample introduction systems that convert complex samples into simple, appropriate gases for specific analyses. The sample introduction system can handle a variety of different sample types: solids, liquids, gases, and there are four primary ways of introducing a sample into an IRMS mass spectrometer. The most common and useful sample introduction systems include the elemental analyzer for bulk sample analysis, gas and liquid chromatography for compound-specific analyses of volatiles and polar samples, and a gas preparation system for headspace and whole sample analyses. An important aspect of IRMS systems is their flexibility and the ability to connect multiple different sample introduction peripherals to a single mass spectrometer. And at Thermo, we do this using a universal continuous interface called the ConFlow 4. In the next few slides, I'll give you a brief overview of these systems before then going on to examples and applications. The elemental analyzer is designed to take an entire or bulk sample and process it for several different isotope systems in a single analysis. For example, it's possible to measure the carbon, nitrogen, and sulfur isotopic composition of a single wood sample in less than 10 minutes. The sample, either solid or liquid, is combusted with oxygen to form CO2, N2, and SO2 gas that are then separated using a GC column before being analyzed on the IRMS. Similarly, oxygen and hydrogen can also be analyzed using high-temperature thermal conversion, or pyrolysis. The EA IsoLink is a very flexible and powerful sample preparation system that can be used on a wide variety of different sample types, many of which we will see in a few upcoming slides. There are two different sample preparation or inlet devices that can be used for compound-specific isotope analysis, which is simply the isotope analysis of specific compounds that make up a sample. For volatile compounds, we use gas chromatography to separate individual compounds on column prior to converting each eluted compound to a simple gas for isotope ratio analysis. Unlike the EA IsoLink, or rather, Just like the EA isolink, the conversion is done using combustion for carbon and nitrogen isotopes, or pyrolysis for oxygen and hydrogen isotopes. But unlike EA isolink, with compound-specific analyses, we can only measure one isotope system at a time, for example, carbon or nitrogen. But what we gain with this is isotope information for each individual compound in a complex sample, which gives us a much more nuanced, in-depth information and a better fingerprint. Another way of doing compound-specific analysis, in this case for non-volatile or polar compounds, is liquid chromatography, which allows the separation of individual compounds within a complex liquid sample prior to processing it by chemical oxidation instead of combustion. And this produces the simple gases for carbon isotope analysis on the IRMS system. This IRMS system has big application in honey authentication analyses, but also in different studies and investigation of metabolites where information on the compound-specific level is required. The gas bench 2 is a solution for analysis of gases in headspace after equilibration. It's useful for addressing oxygen and hydrogen isotope fingerprints of liquid samples, for example, juices and wines. As well, it's useful for analysis of carbon isotopes in ambient air or breath samples, for possible addressing different questions in the field of medical diagnostics or climate studies. Other important and common applications include analyzing nitrogen in water for addressing water pollution sources, something we'll talk about a little bit today, as well as carbonate analysis for addressing paleoclimate research questions using carbon and oxygen isotopes. Now that we know how we can detect isotope fingerprints, it's time to show you how they're actually used, in this case for addressing authenticity, origin, or history questions in different materials. Today we'll start with the food and beverage investigations. Complexities in food and beverage supply chain, from production through to consumers, have presented significant and at times relatively easy opportunities for economically motivated fraud. Such activities affect consumer confidence and product brand reputation, and then have financial consequences. Consequently, there's an increase in retailer and consumer demand to see proof that food and beverage products are what the label claims them to be, including origin, authenticity, and ingredient verification. And this can all be done using isotopes. The isotope fingerprint in food and beverage products is source region and often process specific, which means that products can be differentiated based on geographical region, for example, coffee, sugar, cheese, botanical processes, soil and fertilization processes, as well as fraudulent practices. Carbon isotope fingerprints carry a botanical origin signature, meaning a signature related to photosynthesis, and it can be used to track adulteration and mislabeling of foods. Nitrogen isotopes carry a signature related to soil processes and soil fertilization, which means that they can be used to identify products that have been mislabeled. Sulfur isotopes are linked to local soil and geological conditions, such as the proximity to an ocean shoreline. It can therefore be useful in identifying geographical origin in food and beverage products. And of course, oxygen and hydrogen isotopes, fingerprint, are useful for local regional rainfall. And that gives us the possibility to identify beverage adulteration as well as geographical origin. Here you can see a list of official methods that use isotopes for food authenticity investigation. As you can tell, isotope analysis solutions for bulk or compound-specific analyses can be performed on different kinds of samples and deliver information about adulteration or geographical origin. And let's have a look at a few examples. When we talk about flavors, and especially essential oils, what we are talking about are complex mixtures of volatile and aromatic compounds obtained from plant materials such as flowers, herbs, wood, fruit, but they can also be derived from synthetic material. Authenticity control of flavors and essential oil often comes down to analyzing a specific compound, and we have a few examples. Menthol, for example, is a basic ingredient of mouth fresheners, food, cosmetics, and many more products widely used in everyday life. Menthol can be obtained from natural sources, such as mint oil produced by steam distillation, or it can be made synthetically through several different synthetic pathways. Authenticating if menthol originates from natural or synthetic sources can be done using carbon and hydrogen isotope fingerprints. In this study, in the top left-hand corner, 10 menthol samples were analyzed. As the data shows, by using multiple isotope approach, we can clearly differentiate which of the samples were natural and which were of synthetic origin. The natural samples in green and circled have a very narrow range of isotope ratios and are distinct from the other samples. There are multiple synthetic pathways for producing menthol, so the synthetic samples have a much wider array of isotope values distinct from the natural samples. Bergamot is a hybrid of bitter orange and lemon. Bergamot trees are cultivated almost exclusively along the southern coast of the Calabria region. More than about 90% of the world production of bergamot comes from this region, at least. However, small numbers of bergamot grow in other countries, such as Greece, Morocco, Iran, Argentina, and Brazil. Bergamot fruit is primarily used for the extraction of its essential oil, employed in perfume, cosmetics, but also food. The chemical composition of bergamot essential oil has been widely investigated and is well known. The characteristic flavor of citrus oils is mainly provided by the compounds listed on the x-axis of the graph in the left-hand corner. The carbon isotope fingerprints of these individual compounds can be used to distinguish between authentic and non-authentic commercial samples. Additional investigations of bergamot oil using GC-IRMS also reveal that this methodology is able to not only detect the presence of adulterants in samples, but also to discriminate the bergamot oil samples according to their geographical provenance, and therefore to be able to say where they came from. Honey is subject to fraud by adulteration with low-price sugar syrup addition. Sugar cane and corn syrups, the most widely used adulterants, have distinctive carbon isotope fingerprints because both sugar cane and corn are C4 plants, in contrast to most honey, which is derived from C3 plants. Consequently, carbon isotope fingerprints can be used to identify adulteration of honey that results from the addition of exogenous sugars, because carbon isotope fingerprint of the bulk honey and proteins within the honey is unique. Additionally, we can use compound-specific analysis, or LC-isolink, of sugars in honey to accurately detect lower levels of sugar adulteration or addition. Ensuring that wine is compliant with legal regulations is a very common use of isotope fingerprints. It serves not only consumer protection with respect to increase in globalized wine market, but also wine producers and traders to offer wines of high quality, reliable authenticity, and therefore high price. There's also political and economic objectives to each wine producing country to market internationally well-reputed wines. A common example of wine adulteration that we can detect using isotope fingerprints is the addition of water or juices. The watering technique may be used to reduce alcohol content and increase profits by producing more bottles for sale, and thus reduce tax and customs duty liabilities on exported products. The graph shows an example of wine adulteration by the addition of water, which is detected using the change in oxygen isotope fingerprint. A genuine red wine sample was measured initially to provide the baseline before a sample was sequentially adulterated by adding water. Oxygen isotope fingerprints, or oxygen isotope ratios rather, change with the percentage of water that's added, as you can see in the graph. And this is one of the official methods for detecting wine adulteration. The last example of beverage analysis I want to share with you is about tequila. The blue agave is a native plant to the Jalisco region of Mexico, and it is an important economic product that by law is the only one allowed to be used in the production of tequila. The challenge we will address is about detecting tequila purity and potential adulteration and product mislabeling by the analysis of carbon and oxygen isotope fingerprint of ethanol. The data in the graph at the upper left display carbon and oxygen isotope values that allow us to differentiate pure tequila in the right-hand corner in blue, original mixed tequila, and different sources of sugar, both corn and cane. Why is it possible to use carbon isotope fingerprints in this case? It's because photosynthetically, agave tequiliana is part of the CAM plant group, meaning it has a very well-defined carbon isotope fingerprint of -12 per mil to -14 per mil. So it's a pretty restricted, narrow range. During plant growth, biosynthesis of organic molecules in plants requires water that comes principally from rainfall, which also makes oxygen a powerful fingerprint in this case. Another type of forensics investigations are related to criminal forensics, and we'll have a look at a few examples. Isotope fingerprints in forensic materials are related to natural processes and geographical regions, and can define differences in sample materials, looking at botanical variations, for example, in wood, skeletal remains, dietary and food web variations in skeletal and animal remains, as well as geographical location for skeletal remains, narcotics, explosives, etc. This table provides a non-exhaustive summary of isotope fingerprints in forensics applications. These natural processes can be traced using carbon, nitrogen, sulfur, oxygen, and hydrogen isotope fingerprints encoded in the sample materials, just as we used for food authentication. Using isotope fingerprints makes it possible to determine similarities between different drug seizures and authentic material, and to allow trafficking routes to their original source to be identified. The same principle can be applied to other criminal materials such as explosives, artifacts and gemstones, human remains, animal migration, oil spills, synthetic drugs, arson investigations. There's a wide range of different applications for the use of isotopes in forensics. Also, in the case of explosives, these isotope fingerprints trace factory production, efficiency, and processes as well. So let's look at a few examples. In this study by Ellringer and others, a model was developed to test the origin of humans based on hydrogen and oxygen isotope fingerprints in hair across the United States. The study assessed the relationship between hydrogen and oxygen isotopes in human scalp hair and local tap water and diet. We know that hydrogen and oxygen isotopes of precipitation of water vary along geographical gradients, and this results in local tap water hydrogen and oxygen isotopes, which when consumed by humans will result in a signature of the tap water being used by the body for, in this case, the synthesis of keratin in the hair, or keratin in the hair. The hydrogen and oxygen isotope fingerprint maps, or we call them isoscapes, provide an overview of the expected composition of human hair across the United States of America, with the geographical distribution based on the hydrogen and oxygen isotope fingerprints of tap water. There are assumptions about general dietary input as well, but these hydrogen and oxygen isoscapes can provide information on human diet, movement of individuals, and as a basis for identifying the origin of human remains. Drug abuse, drug production, trafficking, and supply are major global issues, and cocaine is a widely used narcotic. Understanding the geographical region that narcotics come from, in this case cocaine, has the potential to provide significant insight into narcotic movements. For cocaine, this requires the ability to trace the cocaine back to the original coca growing region. In this instance, the isotope fingerprints of coca is preserved during the cocaine synthesis process, meaning that the isotope fingerprint of cocaine are directly related to the area where the coca was cultivated, providing a clear geographical origin tool, especially given hydrogen and oxygen isotope fingerprints are related to local rainfall. Consequently, this study was able to identify the origin of cocaine as coming from specific coca growing regions in South America, in particular Colombia. In this study by Carter and others, the MDA and MDNA extracted from ecstasy tablets were analyzed to determine whether their isotope fingerprints could allow tablets to be linked to a common batch and consequently to be differentiated between production batches. The carbon isotope fingerprint of natural products is determined primarily by the carbon fixation mechanism of the parent material. Hence, little variation is seen in compounds with identical biosynthetic pathways, meaning variations are likely associated with the synthetic process from the parent material. For the nitrogen isotope fingerprint, this variability can be attributed to the reductive amination process, whilst the hydrogen isotope fingerprint is known for reflecting moisture availability during biosynthesis and exhibits greater variations than the other stable isotopes in natural products. The combination of carbon, nitrogen, and hydrogen isotope fingerprints in this study allowed different batches of ecstasy tablets to be identified and also allowed them to be the tablets from different batches to be grouped. In this study, by Benson and others, the isotope fingerprints were employed to determine whether organic peroxide explosives could be used to determine differences in starting material manufacturing processes of explosives such as triacetone triperoxide, which is abbreviated TATP. Organic explosives such as TATP are increasingly used due to regulation of constituents for traditional inorganic explosives, such as ammonium nitrate, as well as the availability and low-cost nature of peroxide precursors, which include hydrogen peroxide and acetone. The ease of manufacture of organic explosives, as well as the sensitivity of the organic explosives, meaning that no detonator is required for them. Consequently, identifying and tracking explosives to support counterterrorism efforts is critical for national and international security. In this preliminary study, a small batch of TATP samples were analyzed for their carbon, hydrogen, and oxygen isotope fingerprints. From the figure, it is clear that the origin of the triacetone triperoxide samples can be differentiated from one another, allowing their origin and manufacturing processes to be identified. Pharmaceuticals are produced in high amounts at various sites with different prices and different formulations. Therefore, it's essential to the producers and consumers to distinguish the point of origin between originals and generics. Aspirin, or acetylsalicylic acid, is a leading position in the prescription-free therapy of pain, fever, inflammation. The isotope ratios for each compound used in aspirin reveal the history and source of the pharmaceutical, because the ingredients of pharmaceuticals come from natural and/or industrial sources. The parts to build acetylsalicylic acid originate from petroleum and natural sources together. For the salicylic acid, it's petroleum in origin. Furthermore, additives can be added to the pills, such as cornstarch, which is commonly added in different amounts. Corn is a C4 plant with an isotope ratio of approximately -11 per mil, which means it shifts the carbon isotope value of the resulting tablets towards more positive carbon isotope values. A comparison of those carbon isotope values of aspirin in tablets of different origin with the carbon isotope values of complete water-soluble formulations is shown in this figure. And it demonstrates that it is possible to identify different major sources of aspirin. In other words, the additives in the different brands change the carbon isotope value of the tablets in the end. Doping control has received a lot of attention recently, with athletes being challenged to outperform the competition. More than ever, however, they are aware of anti-doping policies, rules, and regulations. And yet, even so, endogenous steroids are still among the most frequently detected class of substances misused in sports. The International Olympic Committee and the World Anti-Doping Agency established suitable methodologies to combat misuse of endogenous anabolic steroids, including isotope fingerprints. Doping control laboratories accredited by the World Anti-Doping Agency obligatorily use methods for the determination of the stable carbon isotope ratios of steroids in urine. Here I have displayed are the results of an excretion study after testosterone administration. One male volunteer was administered 30 milligrams of testosterone orally. Urine samples were collected before and up to 24 hours after administration. Target compounds of exogenous anabolic steroids and their metabolites exhibit depleted carbon isotope values, while the endogenous reference compounds are not affected and typically actually enriched in their corresponding stable carbon isotope ratio. You can see that hours after administration, the endogenous reference compounds exhibit nearly constant isotope values with very small variation. The plot reveals the largest deviation in carbon isotope values for the target compounds from the endogenous reference compounds between about 2 and 6 hours. However, the data demonstrates that testosterone doping can still be identified up to and including 24 hours after the event, utilizing IRMS results of testosterone and its metabolites. Forensics applications are also found in environmental research. There are different ways of tracing pollution and doing analyses in this field, but often just quantifying pollution is not enough. That's because pollution can be defined as the introduction of a contaminant into the air, water, and land systems, but this means that there is a source. Pollution sources are categorized as point source or non-point source. Point source pollution means that there's an identifiable source, such as effluent from a specific factory into a stream. Non-point source pollution means pollution derived mainly from diffuse sources, such as atmospheric deposition. This means that in order to implement preventative measures and limit the damage caused by pollution, it's critical to determine the origin of pollution. And this we can do using isotopes. Carbon isotope fingerprints carry a botanical origin of signature, meaning a signature related to photosynthesis and factory production. It can be used to identify fossil fuel emissions and biogenic burning, mineralization processes, and air pollution sources. Nitrogen isotopes carry a signature related to soil processes and soil fertilization and manufacturing processes, which means they can be used to identify fertilizer tracing, industrial and transport emissions of air pollution sources. Sulfur isotopes are linked to local soil and geological conditions. Consequently, it can be used to identify fertilizer tracing, natural weathering for source identification, as well as air pollution. And oxygen and hydrogen isotope fingerprints are related to local regional rainfall, making it possible to address air pollution source, waterway pollution from nitrates, and biodegradation pathways of organic pollutants. This example is about the compound-specific analysis. Polycyclic aromatic hydrocarbons are a persistent pollutant in air, soils, sediments in general. Many PAHs are toxic, carcinogenic, or mutagenic to organisms and humans, depending on their structure, placing them among the most extensively monitored organic contaminants. PAHs are present in the environment from natural sources, including fossil fuels like coal. They come from volcanic eruptions and forest fires. But in addition, PAHs derive from anthropogenic sources, including a byproduct of vehicle emissions, burning fireplace wood, for example, fossil fuels, and various industrial processes. Pyrogenic PAHs are formed by incomplete combustion of organic material, such as during the fracking process or cracking process of hydrocarbons. Combustion of motor fuels, combustion of wood in forest fires. Petrogenic PAHs are formed during crude oil maturation as a byproduct of vehicle emissions as well. Although the sources of PAHs are generally well known, investigating whether PAHs originate from oil, wood, coal is important in order to reduce the health risk they pose, and that requires source identification. The carbon isotope fingerprint of PAHs are expected to reflect those of original organic material prior to combustion, and therefore can be used to identify their pyrogenic or petrogenic nature. Air pollution, also known as haze events, is a growing global issue that results from high concentration of submicron particles, referred to as PM 2.5, in air, usually in the form of sulfate aerosols and nitrous oxides derived from fossil fuel burning, ozone, volatile organic compounds, that sort of thing. PM 2.5 particles have a high scattering coefficient on solar radiation, and combined with high humidity, reduce visibility significantly. These factors impact the surface temperature of the Earth, thereby affecting weather and climate, and they carry serious implications for human cardiovascular and respiratory health. In order to improve air quality, it's important to identify the source of air pollutants, which can be determined using isotope fingerprints. The nitrogen, carbon, sulfur isotope fingerprints were analyzed from air filters from South Korea using EA-IRMS, the elemental analyzer. The carbon isotope fingerprint shows little variation and was indicative of vehicle emissions. The nitrogen and sulfur results are shown in the figure on the top left. Sulfur isotope fingerprints decreased while nitrogen isotope fingerprints increased as the amount of pollution increased. This increase in nitrogen is principally related to coal combustion and secondarily to vehicle emissions. And the increase in sulfur is indicative of fossil fuel source and not maritime aerosols or biogenic sulfur sources. This means that the obtained values are correlated with coal burning during winter heating in northern and northeastern China. So this is an example of how bulk analysis of a sample filter can help to determine source of air pollution. Nitrate pollution is a major concern in many waterways across the world. From a human perspective, regarding our drinking water sources, the regulation of nitrate input into water is very important because excess nitrate levels can have serious consequences for the environment and our health. Researchers use isotopes of nitrates to determine the source of nitrate compounds in surface and groundwater. Nitrates are composed of nitrogen and oxygen, both nitrogen-15 and oxygen-18 isotope fingerprints, offering valuable indicators about the different formation processes and therefore different sources of nitrates. We can characterize the major sources of nitrate by using both the isotopes of nitrogen on the x-axis and those of oxygen on the y-axis. As we plot up the expected ranges of our major sources of nitrates, those of atmospheric deposition and rainfall, nitrate fertilizers, soil nitrate, and manure, as well as septic tank nitrate. We start to understand how we can use nitrogen and oxygen isotopes from nitrates in order to track their origin and source. And towards the end, just a few words about petrochemical investigations. With the rising demand, oil, natural gas play a critical role in today's energy and economic systems. with a growing need to assure reliable and safe supplies. Oil exploration comes with risk and significant cost of millions of dollars. As exploration is expensive, petroleum companies use multiple criteria for source identification, such as chemical and isotope fingerprinting, to make a decision on exploitation activities. Identification of sources can be achieved because petrochemical materials carry an isotope fingerprint. Application of isotope fingerprints in exploration and exploitation industry allows for differentiation of gas sources, migration, reservoir characterization, but also assessment of maturation and biodegradation processes. Examples of isotope fingerprints in petrochemical investigations are given in this table. By exploring isotopes of different petrochemical materials, such as source rock, natural gas, or crude oil, we can reveal information on origin of the source materials, as well as different processes that occur along the way, going way back to the deep past even. Carbon isotope fingerprints can be used to identify oil to oil, oil to source rock, and gas to source rock correlations. Nitrogen is used to investigate origin of gases and differentiate thermogenic versus biogenic gas. Sulfur can be used for assessing oil source rock correlation and determining the origin or source of the oil. And oxygen and hydrogen isotope fingerprints are used in detection of water sources and thermal events. Petrochemical material, such as crude oil and gas, have their origin in organic materials such as plants. Plants carry an isotope fingerprint derived from using atmospheric CO2 and water for their growth. Once the plants die, this material is deposited and a portion of it undergoes chemical and physical changes under extreme temperatures and pressures, which results in oil and/or gas production. This means that the incorporation of isotope fingerprints such as carbon and hydrogen in petrochemical materials is related to botanical origin, geographical region, and mineralization processes. In crude oil analyses, pristane and phytane, shown in the chromatogram in the top left side, are well-known biomarkers and can provide biochemical information. Their ratio is widely used to provide an indication of the oxicity of the depositional environment, for example. The way to determine if they are indeed from the same source is to measure their carbon isotope value for each individual compound. Natural gas is a fossil energy source with diverse applications, including transport, heating and cooling, as well as industrial processes for the production of plastics and detergents. Isotopic signatures of natural gas show that many petroleum reservoirs have complex fill histories. Carbon and hydrogen isotope fingerprints of light hydrocarbons and CO2 can uncover the history of natural gas accumulations, determining the origin and thermal maturity, which the required information for gas generation. Sampling of natural gas is a fundamental step in preserving the original composition of the gas. The process of sampling is associated with different methods, procedures, and equipment, all of them coming at a high cost. A variety of sampling cylinders is used for the collection of gases. There are tubes, jars, flasks, bags, etc. Further step in the analysis of natural gas for isotope fingerprints is to transfer those gas samples from sample containers into an isotope ratio mass spectrometer via gas chromatography systems. A reliable solution for gas sampling that preserves sample integrity is available in the form of isotubes and isojars as developed and used by the company Isotech. In order to improve the efficiency in gas analysis, we offer now automated solutions for transferring the collected gas from isotubes or isojars to the IRMS system for analysis. Tray holders and isotubes is also available. Another important aspect of petrochemical investigations is environmental forensics. It's important to assess the risk that petroleum exploration, storage, and transport carries. Such studies are an important part of environmental forensics, where isotope fingerprints are used to correlate different fossil fuels-derived pollutants or contaminants in the environment to their sources. Environmental forensics is associated with all stages of petroleum exploration, from exploration to production to field abandonment. Further isotope applications include detecting sediment or maritime environmental contamination and allocating source of, in this case, bird feather oiling to a tanker spill. In this oil spill study case that I present here, we analyzed bird feathers were analyzed, as well as oil from the cargo residue and oil supplies from nature and up on the beach. And as you could see that it's possible to fingerprint that the bird feathers were not related to natural shoreline residues, but were more related to the oil spill itself. So it's probably obvious where the oil on bird feathers come from in the case of a spill, but isotope fingerprints here does help to produce an irrefutable line of evidence from a forensics perspective. So to summarize, stable isotopes are a powerful tool for detecting fraudulent activities. Multiple isotope approaches allows for better identification for point of origin of a product, for addition of extraneous substances, as well as for identifying processes. And isotope fingerprints helps to determine the origin of pollution and provide conclusive answers for forensic and petrochemical investigations. If you'd like to learn more, I invite you to please visit thermofisher.com/isotope fingerprints. And with that, I'd like to thank you and open the floor up to questions.
Thank you very much, Darren, for the presentation.
Thank you.
Bueno, ahora vamos a ver si tenemos algunas preguntas. Con respecto a los certificados, ahora les voy a compartir mi pantalla para dejarle los mails. Vamos a ver. Me refiero. Aquí hay una, pero ya no lo entiendo, no la tengo muy clara. O sea, preguntan si hay necesidad de procesamiento de muestra, de si nos pueden contar algún ejemplo de más profundidad. Darren, do we need to process the sample in some way? Yes, but well, can you give some example of how is the processing of the sample to introduce it in the instrument?
Yeah, it's a good question because it's not just about the instrument. The preparing the sample is really important, and it depends on the type of sample and the type of analysis you want. I think that sample preparation is simplest for the elemental analyzer. It can be literally as simple as taking a piece of anything and putting it into the elemental analyzer, so no sample prep. But if you do compound-specific analyses, there is a lot of sample prep. You might have to derivatize samples in order to make them volatile for GC analyses. But it really does depend on exactly what information you're looking for and what your samples are to start with. But I would say in general, compound-specific analysis requires more sample prep, whereas bulk analysis requires less, almost none.
Ok. Para análisis elemental, generalmente el tratamiento de la muestra es muy poco. Con el analizador elemental se introducen muestras a granel que pueden tener hasta 100, 500 miligramos. Y sí, en esos equipos la preparación de muestra es mínima. Para análisis de compuestos más específicos, Sí hay otro tipo de preparación, por ejemplo, cromatografía de gases. En algunos casos hay que hacer derivatización de muestra que sí requiere eh, un tratamiento mayor de la misma. Y bueno, son varios periféricos y algunos sí requieren preparación, pero en el analizador elemental la preparación es mínima, en ese caso en particular. Vamos a ver otra pregunta. Bueno, esta ya está en inglés. Thinking about globalization and the global movement of chemicals, how is an isotope fingerprint justified in forensic investigation of or drugs, for example?
Hmm. Hmm. Yeah, that's a good question. So I talked about the stable gas isotopes, carbon, nitrogen, oxygen, but we can also add the rest of the periodic table into the same discussion. And so for this, we would use different instruments, but we do have people that use multi-collector ICP-MS, for example, to look at the calcium or strontium or neodymium isotopic composition of materials and use this as a fingerprint. I worked in a case study where we identified the source of salmon fish. That salmon spawn in rivers, and then the fish are the eggs hatch, they grow, they go out to the ocean where they grow up, and we harvest them for food. But the question of where does the fish come from, we used strontium isotope ratios from fish in order to answer that. So we could do the same thing. We can do lead isotopes, strontium isotopes, iron. All the periodic table can, in the right application, be used to help identify where a material comes from and how it was produced.
Sí, hay otros tipos de análisis, por ejemplo, el ICP masas de multicolector, que ahí sí se puede analizar el resto de la tabla periódica. Se pueden analizar, por ejemplo, estroncio, plomo, calcio en peces. Y sí, todos esos análisis nos permiten hacer una investigación completa en todo lo que tiene que ver con el cambio climático, con la contaminación ambiental, por ejemplo.
And
Eh,
as another example, people looking at uranium ore. Where did uranium ore come from? Because there are nuclear questions for
yes.
non-proliferation. You can look at the impurities of the ore. For example, it will contain neodymium and other rare earth elements. And you can use the isotopic composition of those impurities to provide a fingerprint of where that not oil, but ore came from.
Sí, sobre el mineral de uranio, que bueno, que se usa para aplicaciones nucleares, eh, viendo la relación isotópica del neodimio, se puede ver de dónde proviene este mineral. Es una aplicación bastante usada. Pero bueno, en esta presentación no nos enfocamos mucho en esos equipos, sino solo para los de los análisis de carbono, nitrógeno, oxígeno, hidrógeno y azufre. Pero bueno, en termo hay otra línea totalmente, o sea, que puede hacer este tipo de análisis para el resto de la tabla periódica. Ok, vamos a ver qué otra pregunta tenemos. Bueno, primero lo voy a decir en español, que la otra se me olvidó decirle en español. ¿Cómo se garantiza que la referencia es suficientemente pura para detectar la significancia estadística en la diferencia del metabolito con respecto a la relación isotópica en una droga? Yes, Darren. Uh, how, you, how you guarantee the reference is pure enough for detecting a statistical significant difference in a metabolite isotope ratio due, due to a drug?
Yeah, that's a good question. And there are times it might not be
Darren,
statistically
please,
differentiate.
Darren,
Yes.
please you can talk in short sentences so I translate
Oh, sorry.
because if it's too long, I forgot what you said before. Thank you.
Fair, true. Yeah. Yeah. In this case, it can be very difficult. In some cases, the isotope difference is very large and it's easy to distinguish. but in some cases it's very small, and that's not true.
En algunos de los casos, esta diferencia en relaciones isotópicas es grande y es fácil de ver, pero en otros casos es pequeña y es más complicado.
And in some cases, it's not an absolute. It's not like we see an isotope ratio and say, aha. Instead, we're looking for differences from deviations from nature, deviations from expected values.
En muchos casos estamos viendo la diferencia con respecto a productos naturales, las diferencias con respecto a valores esperados.
But for example, testosterone, the presence of testosterone isn't the problem. It's how much is too much and where did it come from? And so there's no isotope value for anabolic steroids. It's the difference between the patient's natural steroid sample composition. And so it's all relative, I think, is my answer.
Sí, que todo es relativo. O sea, yo quiero agregar algo a lo que dice Darren, es que en realidad todos estos valores, lo que se comparan es a referencias. O sea, referencias que, o sea, son valores que ya son estándares que ya están establecidos y lo que se hace es comparar todas estas relaciones isotópicas con esos estándares. O sea, en ningún caso van a ser valores absolutos. Ok, vamos
Mhm.
a ver otra pregunta. ¿Pueden ser usados los isótopos estables para identificar salmón o trucha eh, cultivada versus la que no está cultivada? Darren, can stable isotopes be used to identify farmed versus not farmed salmon or trout?
That's a good question. My answer has to be maybe. I think it would be difficult to say unless the source of the water or the food was different. And so if the isotopic composition of the food or the water that the fish are living in is different than the natural, then yes, it can be used. But if the source is the same, then no.
Sí, la respuesta es quizás, porque si, o sea, la diferencia se va a ver reflejada en si el agua o la comida es diferente. Porque si es la misma, o sea, para estas especies cultivadas o las que no son cultivadas, no se va a ver ninguna diferencia. O sea, eso va a depender del agua y de la comida con que se alimenten.
But if you use multiple different isotopes, it might be possible to say yes or no. Because, for example, nitrogen isotopes say a lot about where in the food web you eat. Do you eat algae or do you eat fish? And so if their source of food is different as well, then it might be possible to use nitrogen and carbon isotopes to say something.
Ok. Sí, también, bueno, si se analizan muchos isótopos, aumenta la posibilidad de poder identificar esto. Por ejemplo, el nitrógeno, que es un componente muy importante, o sea, el nitrógeno es de las proteínas, eh, va a permitir identificar si los peces están comiendo, qué tipo de comida, bueno, están comiendo, valga la redundancia. Ok, vamos a otra pregunta. ¿Es posible determinar contaminación atómica en carnes de peces? Okay, Darren, is possible to analyze pollution in fish meat?
Yes, it is. And we do this all the time. I think in this case, to we can identify the pollution, but then saying where it is from might be possible if there's enough. but there might not be enough. So it might just be possible to say that it's there. Yeah, that's an interesting question. I don't know.
Sí, no, es una pregunta medio ambigua, puede que sí, no, Darren no tiene la respuesta porque sí, va a depender
No.
mucho del sitio. Yes.
But yeah, it depends on the pollution, because certain pollutions will have the enough of an element. So yeah, it's possible. If it's mercury pollution, we can trace mercury pollution using isotopes of mercury, and different organic compounds we can trace. So yes, if there's enough of it.
Ok, sí, bueno, también depende de la contaminación, pero en algunos casos, por ejemplo, contaminación con mercurio, sería muy fácil determinarlo en un multicolector. Vamos a ver otras preguntas. Ok, la composición isotópica del solvente usada en la preparación de muestra o en la fase móvil en cromatografía líquida puede ser un problema para el análisis. Darren, the isotopic composition of solvent using in a sample prep or in a mobile phase in liquid chromatography can be a problem in the analysis.
Correct, absolutely. This is why we use an aqueous phase, not a solvent phase, for the LC isolink.
Ok, en este caso no se usa una fase de solvente para el LC Isolink, que es el módulo HPLC.
Yeah.
But could you give us more detail about this, Darren?
Yeah, so it avoids, there's multiple things that a solvent extraction is harmful for. It's bad for, I mean, you're adding a lot of carbon and hydrogen in the form of an
Yes.
organic solvent, but you're also, that organic solvent is really bad for the mass spectrometer. It does damage to the mass spectrometer. And so we use an aqueous phase to do a separation on an LC column, and then we remove that aqueous phase at the conversion in the oxidation reactor when we create the CO2 gas. And so we recycle that aqueous phase for further
Okay.
extraction. But it's a water-based extraction system.
Sí, o sea, los solventes se eliminan. O sea, el equipo tiene un sistema para la eliminación de todos estos solventes porque sí, si llegan al espectrómetro de masas, además de que van a dar resultados erróneos, pueden dañar el equipo. Ok, preguntan, ¿con el ICP masa se pueden ver los isótopos mencionados? Bueno, esta la puedo responder yo que es rápido. No, estos equipos son para, o sea, los que les mostró Darren, son para relaciones isotópicas de carbono, nitrógeno, oxígeno, azufre e hidrógeno. El ICP plasma masa, que son equipos, por ejemplo, el termo se llama NIOMA, son equipos multicolectores que son los que se usan para el resto de la tabla periódica. O sea, estos isótopos no podrían verse en ese equipo. Igual que en un ICP masas, por ejemplo, no se puede analizar oxígeno o hidrógeno. Ok, vamos con otra pregunta. ¿Es posible usar IRMS al análisis de material particulado en agua marina? Por ejemplo, carbono 13 en fitoplancton, en muestras de fitoplancton para el estudio de procesos de fotosíntesis. Okay, Darren, it's possible to apply IRMS to analysis of particulate material in seawater. For example, carbon 13 assimilation in phytoplankton samples for the study of photosynthesis processes.
Absolutely. Yes. And there you have to separate the phytoplankton from the rest of the sample, but absolutely. And these sorts of studies um, do happen. Absolutely.
Ok. Sí, sí, sin dudas. Lo único es que, bueno, hay que tratar de separar el fitoplancton del resto de la muestra, pero luego se puede analizar sin problemas. Es aplicable en el método en el maíz transgénico. Darren, eh,
Mhm.
this can be analyzed in the transgenic, I don't know if that's the translation, transgenic corn.
Oh, to see if the I don't know if
Did
this
you
has
know?
been done. I don't know.
Okay.
Trans Transgenic corn, is this to see if the corn has been
Yes, yes.
different
Modified.
hybrids of corn?
Yes.
I don't. I would say maybe not in this case. I don't think so, because I think that would you would do more of a genetic analysis there. I just don't know.
Si no sabemos, eso puede que sea algo más análisis genético que un análisis así de relaciones isotópicas. Así que
I mean,
probablemente no.
you could use an Orbitrap to look at variation in metabolites and things of this nature and see if that varies. But I don't know if isotopes might tell you something. I just don't know of anybody who's done that yet or looked
Ok.
at that.
Sí, quizás los isótopos sí pueden decirte algo con respecto a esto, pero no sabemos si hay alguien que haya hecho este tipo de análisis. Quizás un equipo espectrómetro de masas como el Orbitrap también de termo, quizás puede ver las diferencias entre los metabolitos, pero en este caso no sabemos. Bueno, ya, yo les voy a compartir mi pantalla. Darren, can you stop sharing your screen? That I'm going
Oh,
to share
sure.
mine.
Absolutely.
Okay. Well, no.
Did that work?
Mm, no, I don't know. Sí, que les quiero
Is that
compartir mi
better?
pantalla para los certificados. Bueno, los voy a escribir por acá. No sé porque no encuentro cómo compartirla. Ah, ok, ahora sí. Ok, ahora pueden ver mi pantalla. O sea, aquí están los mails. Can you see my screen, Darren?
I can. Mm-hmm.
Ok, it's okay. Bueno, ahí están los mails para contactarme cualquier duda que tengan. eh, y bueno, a los que requieran certificados, los podemos tramitar por allí. Eso son gratis, eso no requiere ningún monto, que me lo preguntaron. Eh, no sé si tienen alguna pregunta adicional. Bueno, aquí tengo otra. Este, ¿Qué tipo de gases se usan en estos instrumentos? Darren, which are
Mm-hmm.
the gases used in these instruments?
Most commonly, carbon, nitrogen, sulfur, oxygen, and hydrogen. And as a gas, they're introduced as CO2, SO2 for sulfur,
Ok,
N2 for nitrogen, and then the oxygen you could measure either from CO2 or from carbon monoxide, CO, and then hydrogen is H2.
Ok, son los tipos de gases más comunes como hidrógeno, dióxido de carbono, nitrógeno, dióxido de azufre. Y bueno, si estaban preguntando pues creo que la pregunta era medio ambigua. O sea, para el funcionamiento de los equipos, bueno, también hace falta helio que se usa como carrier para las muestras. Y los otros son gases de referencia. Preguntan, ¿cuál es el precio aproximado de un equipo? O si es más económico que un ICP Masas. No. Eh, estos equipos son más caros que un ICP Masas. O sea, son equipos más grandes, tienen unos imanes muy grandes para hacer esta separación de isótopos. O sea, es un equipo más caro que un ICP Masas. Probablemente depende de la aplicación, porque como Darren les mostró, hay varios módulos que se le pueden poner al equipo. O sea, está el módulo de cromatografía líquida, el analizador elemental, el gas bench, que es para análisis directamente de gases, por ejemplo. Y, o sea, depende de qué tantos periféricos tenga un equipo, el precio obviamente va a subir bastante. Eh, un equipo, lo más básico, con un solo periférico, igual sí va a ser más caro que un ICP Masas, quizá de un 50% más caro. O sea, pero estos son equipos muy, muy específicos, o sea, muy potentes para hacer lo que hacen, esta determinación de relaciones isotópicas. Bueno, no sé si tienen alguna pregunta con respecto al certificado. Bueno, envíen solamente su nombre, la institución y le enviamos su certificado. No hay ningún dato específico que tengan que enviar. Con respecto a la grabación del webinar, sí, cuando la subamos a YouTube, vamos igual a compartir el link este, para que lo tengan, si lo quieren ver o lo quieren compartir. ¿Podría proporcionar algún detalle o ejemplo acerca de la salida de datos que generan los equipos? ¿Es una planilla Excel? ¿Tiene un puerto USB? No, estos equipos tienen software que son muy, muy avanzados, muy amigables para el tratamiento de todo el equipo. Ahí se va a hablar, le voy a preguntar a Darren que les hable un poco sobre esto. Darren, can you talk a little about the Qtegra? They are asking about the software of these
Hmm.
instruments.
Yeah, so right now the software is what we call Isodat. But they might have heard that we are coming out with a new software, Qtegra, the
Okay.
same software that we use for ICAP, ICP-MS, but modified for gas isotopes. And so, yes, this is something that we will have, and it will be for all gas isotope products. And I don't know, certainly by the end of the year. I don't know how quickly before now, but certainly before the end of the year, this will be something that we have available.
Ok. Sí, por ahora se usa un software que se llama Isodat que hace todo este tipo de análisis, pero pronto se va a hacer un upgrade al Qtegra, que además es el mismo software con el que se manejan los equipos de ICP Masas o ICP óptico. O sea, ya es un software que se va a utilizar para manejar toda la línea de IRMS.
Mhm. And the good thing about the software is that, for people who require compliance, it has, for example, CFR 21 compliance, which in the US is important. Um, and it will cover all the products, and it should be an improvement in terms of performance, how it's used, and the ease of use. But yeah, I think we'll have more on this in the next 2 months.
Sí, sí. Este, va a haber nueva información, perdón, sobre estos software en los próximos meses. Bueno, aquí vemos, están preguntando, sí, bueno, cuando envíen los correos, igual ahí vamos, o sea, no hace falta que nos den el correo porque ya va a estar en el correo que envían. Con el nombre es suficiente. ¿Dónde suelen publicar los seminarios que brindan? En YouTube, en nuestro canal de YouTube. eh, bueno, tenemos 3 canales para las diferentes empresas que conforman todo este conglomerado. Eh, de todas formas, a todos los que se registraron, automáticamente le vamos a estar enviando el link con, con toda la información. O sea, con el link a YouTube. Así que por eso no se preocupen. De todas maneras, si quieren ver todos los videos y los webinars anteriores, están en el canal de Soluciones Analíticas, Analítica del Pacífico y el Grupo Analítico Centroamericano. Bueno, creo que ya no tenemos más preguntas. Eh, muchas gracias por, por haber asistido y nos vemos en el próximo webinar. Thank you, Darren, for your presentation. It was great and very clear. And
I'm happy.
when we hope to have you some other time.
Anytime. It's my pleasure, Gonzalo. Thank you.
Well, bye. Chao. Nos vemos la próxima.
Ciao. Have a good day.